AdoB, which is our approach for verifying benign and Byzantine consensus algorithms in a general way. This work is led by Honoré, collaborating with me, Yoonseung Kim, Ji-Yong Shin, Jieung Kim, and advised by Professor Zhong Shao. Oops. Okay, so I'll begin with a review on the definition of the consensus problem. It's a central problem in the field of distributed systems. The goal here is to make a group of networking machines agree on a linear sequence of values. And these values are usually submitted client requests. And so it's the underlying technology of all existing blockchains and other distributed systems. So we usually want these algorithms to satisfy two properties. The first one is safety, which means that in the logs received by each machine, there cannot be any forks. The second property is liveness, which means any machine can always successfully append new values to the consensus log. And of course, we also want these systems to satisfy fault tolerance, which means that if a subset of the machines fail, the system as a whole can continue to operate. Now, in any distributed system, you need to rely on a certain communication model to make progress. And in the field of consensus, there are three kinds of commonly used communication models. The first one is asynchronous, which says messages can take arbitrarily long to arrive. The second one is synchronous, which says messages must arrive within a certain bound. This is an easy model, but it's too strong. So most people use a third model called partial synchrony, which means there is an unknown time point called GST, such that before GST, the messages can take arbitrarily long to arrive. But after GST, they must arrive within a certain bound. And this is a very practical model, but we only give liveness guarantee after GST. Now, by a very well-known theorem in the 1980s, there is no deterministic solution to asynchronous protocols. And so all existing solutions require some kind of probabilistic reasoning, which is difficult. So we will not consider them in this work. So we will exclusively focus on synchronous and partially synchronous algorithms. Now, we also need to consider the fault models of consensus. And in this field, we typically divide between two different kinds of faults. The first one is called a benign fault, which basically says you crash and then you do nothing. You neither receive new messages nor send out new messages. And in this case, it's known that you need at least 2f+1 nodes, where f is the maximum number of faulty nodes, to ensure liveness. There is a second kind of fault, which is called a Byzantine fault, which says if you fail, you become faulty, and then you can inject any message you like into the network system. And in this case, it's known that you need at least 3f+1 nodes to ensure both safety and liveness. Now, the traditional thought on this field is that these two kinds of faults are very different from each other. And to verify each of these algorithms here, you have to draw up a long list of invariants satisfied this particular algorithm individually, and then verify them. But the problem is, how do you come up with the list of invariants in the first place? This is a non-trivial task. So we are not very satisfied with the situation. We ask the following question. Is there a good abstraction that allows proving safety and liveness of all these different protocols by refinement? Well, but first, why do we want a refinement-based model for all different kinds of faults? The first reason, of course, is that there are indeed strong structural similarities between these algorithms. For example, Lamport has once written a paper called Byzantizing Paxos, where he informally described the idea that PBFT is a refinement of Paxos, but he didn't carry out this idea formally to the very end. The second reason, of course, is that this gives us simpler and more reusable proofs, because the refinement model will tell you what kind of safety restraints you have to satisfy on your network model, and you just need to prove those constraints instead of coming up with others on your own. Well, the third reason is that in certain cases, you do need to tolerate mixed faults. For example, there is a very famous blog post by Cloudflare. They are using a Raft protocol, which is a benign fault protocol. But it turns out that in certain cases, you do need to add a certain defense against the Byzantine faults. Otherwise, you still don't get deterministic liveness, as is shown in their blog post. So this leads to our contributions. We propose AdoB, which is a refinement-based framework for all kinds of consensus algorithms. And we claim that it elegantly unifies benign Byzantine fault tolerance. And by a natural generalization, we can also support proof-of-stake fault tolerance, which is popular in blockchains. And we gave 2 case studies for our model. The first one is a generalized version of the Jolteon consensus protocol. We will show that it is possible to parameterize this algorithm so it can tolerate either benign fault or Byzantine fault or proof of stake. The second case study is Fast Paxos. It's a benign consensus protocol with a slightly unusual structure. And we claim that it can be interpreted as a limited kind of Byzantine fault. So due to limited time, I will only give a quick overview of AdoB and our implementations of AdoB. And for the full details, please refer to our paper. So the general philosophy of all our works on atomic distributed object is that we want to understand consensus algorithms by refinement. And previously, we did this on a number of benign fault tolerance algorithms. For example, there was AdoB work, which was on reconfiguring Raft algorithm. But that was not covering Byzantine faults. So here, the AdoB is essentially extending ADO work to the Byzantine realm. The idea is that we still use a cache tree-based view to represent the internal state of consensus algorithms. So shown here is an example of a cache tree where all these shapes, we call them cache nodes. The details are not very important at this point, but the general idea is they encode the state of the consensus log. Now, we observe that in all these protocols, they basically all execute in rounds. And in each round, there is a single node that is shown as the leader of that round. And only this leader is trying to make the network make progress. Now, this leader, we observe that it is essentially doing 3 things in sequence. Which we call pull, invoke, and push. The pull operation is essentially we have to update the local consensus log of the leader to the latest version. Actually, not the latest version, but one of the latest versions because of potential failures. And then the leader now proposes its own additions to the consensus log, and that's called invoke. And finally, we try to commit the changes to the log. And if this succeeds, then the future leaders are guaranteed to see the changes. But if it doesn't succeed, then we see a network failure. And the future leaders may or may not see your proposed changes. So here's an example of AdoB in execution. And suppose for now, we only focus on benign consensus. Initially, the cache tree is empty. We have only a single node, which we call the root cache node. Now, the first round begins, and of course, the first leader comes in and has to obtain an up-to-date consensus log. Well, at this point, of course, the consensus log is empty, so it can only, this eCache can only be connected to the root cache node. Then it proposes its own changes to the consensus log. Notice that here, the proposed value only needs to be signed by the leader because it's benign consensus. We don't expect the leader to try to actively fork the consensus log. Now it attempts to commit its changes to the consensus log. Now here observe that this Ccache requires a voter of a set of quorum of nodes. And the reason is that we need quorum overlapping to ensure the future leaders will see the proposed values. And this concludes the first round. Now the second round begins. And the second leader will come in and also do the pull, invoke, and push sequence again. And this is essentially what occurs in the happy case where no network failure occurs. But it's also possible that due to network failure, you don't see the progress in a certain round. And in this case, there is a component called the pacemaker will kick in and create a T-cache. This T-cache basically represents a timeout. We say, the nodes say, we cannot tolerate a longer delay, so we will just move on to the next round. Now, obviously, this T-cache would represent a blockage to liveness. So AdoB, from here there, we naturally derive a liveness criterion for consensus algorithms. We say, after GST, the honest leaders have to keep making new operations in higher rounds, but they must not create new T-caches. And if we can prove from certain network level safety assumptions that this is the case, then we obtain liveness of the whole protocol. Now, what about Byzantine faults? The key insight we make in this work is that for benign and Byzantine fault tolerance, there is only one essential difference, which is that the Byzantine leaders may try to actively fork the consensus log. So in this case, we make the M cache, we add the criterion that the M cache must be signed by a quorum of nodes. So as shown here, the M cache voter has changed. So how do we unify this difference in behavior? Well, we introduce a new abstraction called the M quorum, which is our key to unifying benign and Byzantine consensus. M quorum is essentially just a round-specific committee that prevents leader proposal equivocation. And we here make some general observations on this abstraction. First of all, this M quorum is round-specific, so you don't need overlapping between different rounds. And within each round, it's sufficient that they overlap on at least one honest node. So we can parameterize this M quorum in different ways for benign and Byzantine protocols. For benign protocols, we only require the M quorum to contain the leader. Since all these sets overlap on the leader, and the leader is not Byzantine, it's guaranteed that the log will not fork. But in the Byzantine case, we do need at least 2/3 of the nodes to sign on the proposed value. And there is a natural generalization to proof-of-stake consensus. We say we give each node a weight, and we assume that 2/3 of the weights are held by non-Byzantine nodes, and that is sufficient to guarantee safety. So we now look at the case studies we made using the AdoB model. The first algorithm we verified is Jolteon. It's short for generalized Jolteon. Jolteon is a Byzantine fault-tolerant algorithm, but we observed that there is an easy way to parameterize this algorithm. Basically, we make the first phase only require signing by an M quorum, and the second phase still requires signing by the 2/3 of nodes. And in this case, we can make it tolerate either benign or Byzantine fault. If you say only tolerate benign fault, then it degenerates to multi-valued Paxos. But if you make it also tolerate Byzantine fault, then it degenerates to the original Jolteon. And in between, you can make it tolerate a mixture of faults. And in all cases, we still give you safety and liveness proofs. We also did experiments on Fast Paxos, which is a benign consensus algorithm with a slightly unusual structure. Basically, the leader can say, I don't want to pick a value. We make the voters pick a value for me. So it sends a special any command to voters, and then voters are free to commit any value they want. And this is essentially just a limited form of a Byzantine fault. So we observed that it's easy to parameterize AdoB to do a refinement proof for Fast Paxos as well. The basic idea is for M quorum, we make them any set of at least half of the voters, so they overlap on at least one member. And for the quorum, commit quorum, we still need a set of at least 3/4 of voters. And here we summarize the proof effort we did with these protocols. When this project began, we weren't quite sure how to model Byzantine faults, so we took the route of doing multiple layers of gradually descent into the network model of Jolteon. This led to a few detours. If we do it today again, we would probably reduce the effort by half. And as shown here, for Fast Paxos, we can prove its safety and liveness with much less effort. So the conclusion of this work is essentially that there are very strong structural similarities between benign and Byzantine fault tolerance. And we can formally exploit this similarity to simplify the task of verifying these new consensus algorithms. And to demonstrate this, we introduced several case studies of safety and liveness proof of fault tolerance algorithms. And this is also one of the first mechanized liveness proofs of any consensus algorithm. And for the details, please check out our website. And that concludes my talk. Thank you.
Your proof experience here. Did you learn anything about writing proofs that might be applicable to other kinds of verification projects? Or are there changes you would make to Coq to make it much easier next time?
Well, so when this work began, we were very much doing a reordering proof, which is basically we reorder the events in the trace over and over again, and then make them gradually behave like an atomic trace. We figured out this was in fact not the best way to do refinement proofs. First, because it's simply painful to reason about reordering our traces. And second, this reordering actually obstructs liveness proofs, because in reordering the trace, you are destroying certain temporal information. And so if we do it today again, we will probably not go along a line of, say, reordering these individual events, and we will just do a much simpler refinement proof. Yeah.
Other questions?
So, probably doing...
One thing I was curious about looking at the paper, you talk about in your liveness guarantee, if I understood correctly, it's about ensuring that eventually the protocol will continue.
Yeah.
I wonder if you can say anything about bounding the number of steps required.
Well, in all these protocols, it depends on the, so as shown here, you need to make certain assumptions on message delivery. The assumption we make is, say, after GST, all the messages must be delivered within delta, where delta is a parameter of the algorithm. And then the number of steps, it's formally stated in terms of this delta multiples. And this depends on protocol. For the Jolteon protocol, it's 2 phases, so it's 4 delta, where each phase consists of leader sending out and then the voters responding back.
You're welcome to step up to ask questions if you have questions. Okay, let's give you the speaker one more round of applause. If the next person can come set up, please.